So this class will discuss RC circuits, the charging equation and the discharging equation, and some simple circuit questions based on that. Just a moment. Okay, consider a circuit like this. Now, one of you tell me, if there's a capacitor and a cell, consider it as an ideal cell. Cell EMF is V, capacitance is C. Assume it is initially uncharged. When we close the switch, how much charge will you finally see on the capacitor? How much charge does the capacitor get? And a capacitor, Q equal to CV. So you'll see CV on this side minus CV on this side. Fine. So battery does this job of pulling electrons from one plate and depositing them on the other. Okay. But see, initially when the capacitor is uncharged, it's easy, very easy to take an electron from this side and deposit it on the other side because there's no potential difference developed yet. So the first electron can easily be transferred. Fine. But as time passes, as charge gets accumulated on these plates, positive charge on the left side, negative charge on the right side, okay, it becomes difficult to remove an electron from one plate. Okay, from the positively charged plate, the battery has to remove the electron. Electron will experience attraction to the positively charged plate. So it becomes difficult to remove it. And it has to deposit on the other side. The other side plate is already negatively charged. And you have to force an electron to go and sit on that negatively charged plate. Okay, so that also requires some energy. We know this process consumes energy, how much energy is stored in the capacitor. We have done that. Okay. But see, as electron flows through that wire, okay, through that battery also cell, it experiences some resistance. Fine. In a real situation, there will definitely be some resistance. Okay. So let's consider the circuit that you see on the left side. Assume the capacitor is uncharged, and let's say R is the resistance in this circuit. Okay. Battery EMF is V, ideal cell we are taking. Okay. The moment this switch is closed, what the battery does is it starts pulling electrons from the left plate. So it makes the left plate positively charged and it deposits electrons on the right plate. So you can imagine electrons moving like this. Through the cell onto the other plate. Okay, so electrons here are flowing anti-clockwise. That means current is flowing clockwise. So basically, the moment you close the switch, the battery drives current in the circuit. Okay, electrons are flowing anti-clockwise, so current flows like this. Let's call the current as I. As time passes, charge gets accumulated on the plates of the capacitor. Positive charge appears on this plate, let's say Q. Negative charge appears on the opposite plate, say minus Q. Okay. So let's say the switch is closed at t equal to 0. Then at a random instant, situation will be like this. There'll be a current flowing in this wire, some charge on the capacitor, and it's still getting charged. Okay. We know that the capacitor should get a charge of Q is equal to CV ultimately, but it takes time for that much charge to get accumulated on the plates of the capacitor. Fine. There is resistance in the wires, and also as charge gets accumulated on the plates, it becomes difficult to transfer the next electron from one plate to the other. So it's a time-taking process. And that is what we are going to discuss now. That is what we are going to derive now. How much time it will take to accumulate how much charge on the capacitor. Okay. Right. So at a random instant, let's say this is the situation. Seshank, tell me, if we start from this point and move clockwise along this loop, how to apply KVL to this loop? Like, how do you write the KVL equation?
First minus IR.
The first element you come across is the resistance, and you are moving in the direction of current, so minus IR. Okay. Continue.
Minus Q by C.
Okay. Can you tell me the general formula for writing potential change across a capacitor?
The negative of the first plate divided by capacity.
Okay, negative of charge on the first plate divided by C. Now, as you move clockwise along this loop, the charge on the first plate that you come across is Q. So negative of Q divided by C, and continue moving along the loop. The next
Plus
element, plus V. You're going from negative terminal to positive terminal. So plus V is equal to 0. That's the KVL equation for this loop, correct? Now, what is our aim now? Our aim is to derive charge as a function of time and current as a function of time. We want to find out how much charge gets accumulated on the capacitor in how much time. Okay. Now, consider this KVL equation itself. There is no T term in it. Okay, there is current, there is charge, there is V and C, but there is no T term in it. So using this equation, you can't directly get charge as a function of time. Can any of you tell me how to bring time into the equation?
current is charge per unit.
Okay. Current by definition is rate of flow of charge. Fine. Now see, generally, like from the definition of current, we write I is equal to dq by dt. That's fine. But here we have assigned the symbol Q to charge on one plate of the capacitor. Okay. And the symbol I to current in the wire, that wire that you can see. Now, are you sure that in this case, dq by dt will be the current? That you have to check. See, I is equal to dq by dt is the definition of current. That's fine. But here Q means something. Q means charge on the capacitor plate, and I is the current in that wire. But see, since the wire is directly connected to this plate of the capacitor, I here, which is basically the rate of flow of charge, will be equal to the rate of change of this charge, Q, because all the current is directly sending charge to that plate itself. Now, when can you not write I is equal to dq by dt in this case? For example, you can consider, suppose there's another branch through which some current can pass. Then it won't be correct to write this current as this dq by dt. Okay, current by definition is rate of flow of charge, but the current flowing in this wire, is it same as the rate of accumulation of charge on the capacitor is what you need to check, because you have assigned the symbol Q to something here in this situation. Okay, fine. Now, if there's only one branch like this, then yes, if I is the current and it's flowing this way, then it will be equal to the rate of increase of positive charge on the plate of the capacitor. So we can write I as dq by dt in this case. So then it becomes, the equation becomes minus R dq by dt minus q by c plus v is equal to 0. Okay. Our aim is to get charge as a function of time. No? So we have to keep charge terms on one side, time t terms on the other side. Let us do that. So if you send q by c to the other side, you get q by c minus v is equal to minus r dq by dt. Or the left hand side, I'll write it as q minus cv divided by c. Simple derivation only. And then you can write dq divided by q minus cv is equal to minus dt divided by rc. I just adjusted this equation. This minus r was sent to the denominator here. dt is sent to the numerator here, and the q minus cv goes to the denominator here, such that all the q terms are on one side and t terms are on the other side. Okay. Now we just have to integrate this to get charge as a function of time. Can one of you tell me the integral of 1 by q minus cv?
ln q minus
Ln q minus cv, correct. So we can say that we have to substitute the limits here. Initial charge to the final charge is equal to right hand side integral R and C, resistance in the circuit, and C is the capacitance of the capacitor. They are constants. You can put it out. Integral dt simply becomes T. So minus T by RC. And limits here will be from 0 to T. Or T initial to T final also you can write. Not an issue. Okay. Okay, let us put it that way for now. T initial to T final. Okay. Now, if the capacitor is initially uncharged, Q initial will be 0. Let's say final charge is some random value Q. Initial time, take it 0 because we assumed the switch was closed at T equal to 0. Final time, let it be T. So you can get charge Q at a time T. So substitute limits now. Ln of Q minus CV. Okay. Minus ln. In place of Q, if you put 0, it becomes minus CV. Is equal to minus T divided by RC. Now one of you tell me, what is ln A minus ln B? Ln A by B. So the left hand side becomes fine. Upper limit minus lower limit. Okay. Ln is nothing but log to the base of E, send E to the other side. You get Q minus CV divided by minus CV is equal to E power minus T by RC. So Q becomes CV into 1 minus E power minus T by RC. So what we get here is charge as a function of time, charge on the capacitor as a function of time. Now observe this equation. First observation, at T is equal to 0. Substitute T0 in this. What is E to the power of 0? What is any number to the power of 0?
1, sir.
1. 1 minus 1 becomes 0. So charge becomes 0. That's correct. That makes sense. We assumed the switch was closed at T equal to 0. No, just when the switch is closed, the capacitor didn't have any charge. Okay. The initial charge was like in the limits also we substituted initial charge as 0, and that's what the equation tells us. Fine. Next. As T tends to infinity, how much does the charge become? What is E to the power of minus infinity?
Yeah.
It was not clear. Can you repeat?
0.
0. Okay. E is 2 point something to the power of minus infinity. It's like 1 by E to the power of infinity tends to 0. Now, if this term tends to 0, then the charge tends to CV. So we can't say Q is equal to, we can say Q tends to CV. And this is an interesting observation. So in an ideal circuit with some resistance, okay, it takes infinite time for the capacitor to get fully charged. For the capacitor to get that charge of Q is equal to CV, it takes infinite time. Okay. And we can even draw a graph of this function, charge as a function of time. Basically, what you can observe from this equation is that it is an exponentially, okay, it's not exponential, 1 minus, fine. We know e to the power of 0 is 1, e to the power of minus infinity tends to 0. Okay. So when this value is 1, the charge is 0. And when the value becomes 0, when e power minus t by rc becomes 0, that is at t tends to infinity, the charge tends to Cv. So if you visualize the graph, charge on the capacitor as a function of time, it starts from 0. And as t tends to infinity, the charge tends to a finite value Cv. Let this be Cv. So the graph increases, and it tends to touch this line. It will be like this. It touches that line at infinity. Okay, so that is the charge on the capacitor as a function of time. Okay, now some of you may have studied this already. What is this term RC called? No idea? Okay, let it be, no problem. We have
it's time constant.
it's called the time constant of the circuit. We got Q is equal to Cv into 1 minus e power minus t by RC. RC can be replaced with tau. Now, this is not the relaxation time that we had discussed about. Relaxation time has nothing to do in RC circuits. Okay. So tau here is called the time constant. We replaced RC with tau. It's called time constant of the circuit. Okay. Now at t is equal to tau, at a time equal to time constant, how much is the charge going to be? Anyone?
EV into E minus 1 by E.
Okay. So just substitute t as tau there, it becomes Cv into 1 minus e power minus tau by tau, that becomes minus 1. So you can write Cv into 1 minus e power minus 1 is 1 by e. Can any of you tell me the value of 1 by e, approximate value up to 1 or 2 decimals? Okay, it will be useful if you remember that value. Just a moment. Around 1 by 2.7, that will be 0.37, let it be. And 1 minus 0.37 becomes 0.63. Listen, Cv is the final charge that you'll see on the capacitor. That's the full charge. Okay. Now, by the time of one time constant, okay, by that time, the charge that would have accumulated on the capacitor is only 0.63 times of Cv. So you can say that is equal to 63% of full charge. Okay. So in one time constant, the capacitor gets charged by 63%. Okay. Remember this value. You can derive it also, not a big deal. So that's the equation for charge on the capacitor as a function of time. Okay. In this circuit, we took a basic RC circuit, one resistor, one capacitor, and one cell. Okay. Charge will increase non-linearly because the function is CV into 1 minus e power minus t by tau, non-linear function. It will increase non-linearly and it will tend to that value CV. Okay. Let us now write the current equation. Same circuit, we got charge is equal to 1 minus e power minus t by, I'll write tau itself. Now, if you want current here, now we have already checked and confirmed that I is equal to dq by dt. Current in that wire is equal to the rate of change of charge on that plate of the capacitor. Okay, so we just need to differentiate this function to get current as a function of time. Now you'll have to differentiate CV minus CV e power minus t by tau. C and V are constant, so derivative of CV will be 0 minus, again in the second term, C and V are constants, put them aside. You'll need to differentiate e power minus t by tau. Can one of you quickly tell me what is the derivative of e power minus t by tau with respect to time?
Minus 1 by tau e power minus 2.
Minus 1 by tau into e power minus t by tau, because generally d by dx of e power ax is equal to a into e power ax. Okay, so here it's like the power of e, which is t, is multiplied with minus 1 by tau. So in place of a, you have minus 1 by tau. So that comes aside. Okay, you'll get minus 1 by tau here. So effectively the current becomes minus CV into minus 1 by tau e power minus t by tau. Okay, and we know tau is equal to RC. C gets cancelled, minus minus also gets cancelled. Therefore, you will be left with I is equal to V by R e power minus t by tau. Okay, let us observe this equation now. Substitute t as 0 in this. How much does the current become?
V by R.
Substitute 0, e power 0 is 1, so current becomes V by R. Now, this is interesting. When a voltage V or when a battery of EMF V is connected directly across a resistance R, the current that flows in that resistance is V by R. Now here in this circuit, there's a capacitor also. Still, you will see that the current initially is V by R. Why? Listen, initially the capacitor was assumed to be uncharged. If it's an uncharged capacitor, the potential difference across its plates is 0. Means if you call this point as X and this point as Y, X and Y are at the same potential. Okay. Now the battery on the left side is connected to this end of the resistance. On the right side is connected to this plate of the capacitor, but this point and this point are at the same potential. It's like effectively at the initial instant, the resistance has a potential difference equal to V. All the potential difference appears across the resistance initially. Because the capacitor is still not charged, it still doesn't have any potential difference across its terminals, across its plates. Okay, that is why the current flowing initially will be V by R. So when a capacitor is uncharged, okay, since there's no potential difference across its plates, if you're solving any question where you have to find out the current, okay, you can treat the capacitor as a closed switch. Simply treat it as a wire. Okay, when it is not charged yet, and you have to find out the current flowing through it or through that branch. So at t equal to 0, this circuit is equivalent to something like this. You can just replace the capacitor with a wire or a closed switch. Okay. Not just this circuit, any circuit where there's an uncharged capacitor. You can think of the capacitor as a wire if you want to find out current flow. Okay. So this is how the circuit behaves just for one moment initially. The next moment capacitor gets some charge. Then there will be some potential difference across the capacitor. Then the potential difference across the resistor won't be equal to V. It will decrease. Okay, they'll start sharing. Right? That's why the current decreases. You can observe the current equation. There's a power minus T here. As time increases, since the power is negative, the current value decreases. Okay, we'll draw the graph also. Okay, so initially the current is I is equal to V by R. You can call it as the peak current, maximum current, I naught. Okay, in fact, this equation can be written as I is equal to I naught e power minus T by tau. So initial current is I naught. Okay. Later on, as T tends to infinity, I is equal to V by R into e power minus T by tau. No? One of you tell me, as T tends to infinity, what does the current become?
Tends to 0.
As T tends to infinity, the power of E becomes minus infinite. Okay, so it's like 1 by e power infinity, which tends to 0. So current tends to 0. Can any of you explain why that happens? Why does current stop flowing even when there's a battery? See, that's because, as I said, or as we discussed earlier, as charge accumulates on the capacitor, it becomes difficult to remove the next electron from one plate and deposit it on the other plate. But the battery can do it up to a certain extent. Okay. Now, when T tends to infinity, the charge on the capacitor becomes CV. This we had discussed already. Okay, we found it from the equation also. When T tends to infinity, this is how the situation will be. When the charge has become CV, it means the potential difference across the capacitor has become equal to V. That's the EMF of the cell. So all the voltage is going to the capacitor. That means there is no voltage across the resistor at all. The potential difference across the resistor becomes 0. That's why the current also becomes 0. Or you can say it becomes difficult to pull the next electron and deposit it on the other plate. It's impossible. Okay. Effectively, what will happen? This entire branch, all that you see on the left hand side or connected to the left plate, all this will come to one potential and all the other side will come to one potential. That's all. No further flow of electrons. This is what will happen finally as T tends to infinity. So when T tends to infinity, the circuit effectively behaves like this. It is equivalent to current has to become 0. Okay. So the capacitor effectively behaves like an open switch as T tends to infinity. Or in general, in any branch of a circuit, if the capacitor is fully charged, means no further accumulation of charge happens on the capacitor. It means no charge flows in that branch. Okay, so you can imagine the capacitor as an open switch. And there will be a potential difference. You can see the left end of the switch is connected to the cell and the right end of the switch is connected to the negative terminal of the cell. So the potential difference there will be equal to the EMF of the cell. Fine. But I mean, questions like this are quite common. You'll be asked what is the final current in a circuit, initial current in a circuit. Okay. So finally, when the capacitor is fully charged, remember it behaves like an open switch. Initially, when the capacitor is not charged at all, it behaves like a closed switch. Okay, simply like a wire. Okay. And we can even draw a graph for current as a function of time. Initial current is V by R, maximum. And later on it decreases. And current decreases exponentially because you have this equation, I is equal to V by R into e power minus t by tau. So when t is 0, I is v by r. From there, it decreases exponentially and tends to 0 as t tends to infinity. Okay. Now tell me, at t is equal to tau, that means at time equal to one time constant, how much is the current?
Zero 0.63 of I.
Okay. T is equal to tau, it becomes I is equal to I naught e power minus 1, that is I naught by e, and we just discussed 1 by e is 0.37. 0.37 or 0.63? 0.37 only, no? 1 by e. 1
No,
by
sir,
e is
1 by is 0.63.
no, 1 by e is 0.37.
Mm.
You calculate and see 1 by 2.7. How can it be 0.6? 1 by 2 itself is 0.5. 1 by 2.7 cannot be 0.6.
Yeah, yes.
Huh. So in a time equal to one time constant, current becomes 0.37. That is 37% of I naught, of peak current. So from I naught, it comes down to 37% of I naught, means it decreases by 63%. Okay. See, these are slightly confusing to remember, but from the equation, you should be able to tell what happens to the current in one time constant. So let us mark that in both the graphs. At t is equal to tau, let this be the time of one time constant. At t equal to tau, the charge on the capacitor will be 63%, that is 0.63 CV. It would have increased by 63% of the maximum value, or increased to 63% of the maximum value. Whereas what happens to the current in one time constant, the current decreases by 63% and it falls to 37%, that is 0.37 V by R, or I naught also you can write. So let me write that statement here. In charge increases to 63% of peak value or maximum charge, and current decreases by 63%, or you can say it decreases to 37%. Okay, there's a difference, decreasing to something, decreasing by something. They are the same, of maximum current. Okay. So this way you can tell what is the current flowing as a function of time, what is the charge on the capacitor as a function of time also. Let's solve one question based on this. Let this be R, let this be 2R, C, battery EMF V. Okay, let's consider a switch also. Assume capacitor is uncharged initially and the switch is also open. So there's no current flowing anywhere. Right. As soon as the switch is closed, Can one of you tell what happens in this circuit?
The current flows through only the 2R resistance branch.
So you are saying there will be no current in the upper branch. Why?
No. Initially, it flows through both the branches. After steady state, it does not flow through the second branch.
Okay, fine. See, the moment you close the switch, the battery will start pulling charges from one side and depositing them on the other. Now, in the middle branch, or you can see where the battery is connected. The positive terminal is connected here, like once the switch is closed. Positive is connected here and here. Negative is connected on the other side of both the branches. So it's like a voltage V is applied across the resistance 2R, and a voltage V is applied across the RC combination in the upper branch as well. Okay, so movement of charges will happen in both the branches, right? Now, in the middle branch across the resistance 2R, since the voltage is V and it remains V, okay, battery maintains that constant voltage V. So you will see a constant current flowing through it. Positive terminal is connected this way, so there will be a constant current, some current, let's call it I1, flowing in this branch, and you can directly tell I1 is equal to V divided by 2R, because the voltage across that resistance is 2R, V, and the resistance is 2R, so current will be V by 2R. In the other branch also the battery's terminals are connected. So what the battery does is it pulls electrons from this side and deposits them on the other side. If electron is flowing anti-clockwise, like current is flowing clockwise. In that other branch, you can consider a current I2 to be flowing like this. But for I2, due to I2, charge gets deposited on the capacitor plates. Then once the capacitor gets fully charged, I2 will become 0. So I2 is a variable current here. Basically, the branch having the capacitor will have a variable current in it. The other branch only has a resistor directly connected to the voltage, so there will be a constant current in that branch. Fine. We got I1. Can one of you tell me the equation for I2? It's like a battery of voltage V is connected across that branch. How much current will flow in that branch? That's the question.
Sir, is it V by R plus CV?
Can you repeat? V by
R plus C into V.
V by R plus CV. Is that what you said?
Yes, sir.
How can this be? V by R is a current, okay. CV is a charge. This equation is dimensionally wrong. The first term has dimensions of current, second term has dimensions of charge. You can't add them. See, it's just a voltage V connected across a branch having resistance R, capacitance C. How much current will flow in it as a function of time? It's like what we derived earlier. This case only, no, voltage V connected to R and C. Okay. So current I2 will show that behavior that we derived. It will be V by R into, because the voltage we applied is V, the resistance in that branch is R, into e power minus T by tau. And tau becomes RC there because resistance is R, capacitance is C. Okay, it's like you can ignore this middle branch altogether. Same thing, no? What happens in that branch depends on what voltage you apply to that branch. The battery is what drives the charges there. Okay, so it's like battery directly connected to R and C. Okay, and since there is another branch here in between, in that other branch also, the movement of charges will happen. So there will be two currents. The middle branch only has a resistance, so there will be a constant current in it. The upper branch has a capacitor also. Capacitor develops a voltage across it as time passes. Okay, so current will start decreasing in that other branch. I2 current will be a decreasing current. I1 will be a constant current. And from simple KCL, you can say that the net current through the cell is I1 plus I2, which will be the sum of these two. So if you add them, it becomes V by R into 1 by 2 plus e power minus t by RC. Any doubts in this? Okay. So tell me, what is the net current through the cell at t equal to 0? From that current equation you tell at t equal to 0, how much is I?
V by 2R plus V by R.
Just substitute t as 0. If you put t 0 there, e power 0, this becomes 1. 1 by 2 plus 1 is 3 by 2. So 3V by 2R is the initial total current through the cell. The moment the switch is closed, that is the current that flows through it. Okay. Next, as t tends to infinity, how much does the current become? Easy. T tends to infinity, e power minus infinity, this term becomes 0. Current becomes V by 2R. So current initially will be 3V by 2R and slowly it will come down to V by 2R. Now you could have answered this last part like this also. Initially the capacitor was uncharged, right? Just a moment. Initially the capacitor was uncharged. When a capacitor is uncharged and you have to find out current in that branch, I told you, you can treat it as a closed switch, just like a wire. So at t equal to 0, when the switch is just closed, you can just take this as a wire. Now see, the voltage V is applied across 2R and the voltage V is applied across R also. So I1 will be V by 2R, I2 will be V by R. Add both, total current will be 3V by 2R. You can find out the total current like this. In fact, current in each branch also you can tell. Next, as t tends to infinity, the capacitor tends to get fully charged. When a capacitor is fully charged, we have discussed this point also. What can you treat it as?
As open switch.
Open switch. Okay. So imagine there is an open switch here. When there's an open switch, you won't have any current in that branch. I2 becomes 0. I1 is V by 2R, so that net current will also be V by 2R itself. Okay. And like once the current stabilizes, now see, this current is a time varying current. We know that as t tends to infinity, the current tends to stabilize. That state is called steady state. So many times you'll find questions like this. They'll ask you, what is the steady state current through the cell? Or what is the steady state voltage across the capacitor? Steady state means when it is fully charged, what is the current, what is the voltage? That is what they are referring to. Okay. Sometimes they may also say a long time after the switch is closed, what is the current, what is the voltage, what is the charge on the capacitor? Long time means t tends to infinity. And as t tends to infinity, current stabilizes. You can call that as steady state also. Okay. So long time and steady state refer to the same situation. So if you just want to find out the currents in each branch or tell the potential difference somewhere, finally or initially, you can do this. Treat the capacitor as as a wire when it is uncharged. When it is fully charged, you treat it as an open switch. Okay. And generally, whenever you find circuits like this, a cell connected to multiple branches. You can visualize the circuit like this. Like you can assume the cell is connected to each branch separately. This is a general idea. It will be useful in AC circuits also. So you can take this as, like if you want to find out I2, you can assume cell is connected only across that branch. So imagine the middle branch was not there. That way you'll get I2. And if you want I1, imagine the cell is connected only across that middle branch. You don't need to consider all this. And add both, you'll get the total current through the cell. Generally, when there are parallel branches, you can do this. But don't blindly apply. Suppose there is an extra resistance here. Then you can't just take that resistance here and that resistance here. Okay, because then current is flowing in that branch. No, the voltage is not V anymore. When that resistance, this extra resistance, when that resistance is not there, the voltage all the way from here to here is V and it remains V. But when current flows through it, it becomes V minus IR. It depends on how much current is flowing. And how much current flows depends on both branches, not individual branches. Okay, so if there's resistance, you can't do that. Okay, fine. Let us discuss the discharging of a capacitor also. Suppose there's a charged capacitor initially having a charge capital Q on this plate minus Q on the other plate. Assume there's a resistance. Let it be R. Now, the plates are oppositely charged. If you connect them, the opposite charges will combine till the charge on each plate becomes 0. The potential difference has to disappear. Okay, so both plates should become neutral because net charge is 0. When the charges combine, both plates will come to 0, 0 charge. But because there is a resistance, it doesn't allow the charge to move completely freely. Okay, it takes some time for the charge to combine, for the positive charge to combine with the negative charge and become neutral. It takes some time because there is some resistance. That equation is what we want to derive now. Okay, so let's say switch is closed at t equal to 0. Once you close the switch, positive and negative will combine, and you can tell from which side to which side the electrons will go. It's usually the electrons that flow, right? Electrons will move from here to here. It's like electrons are moving clockwise. That means the current will be flowing anti-clockwise. So let's say there's a current I. And since the charges are combining, the charge left on each plate will not be capital Q and minus capital Q anymore. Okay, so this will be the situation. Fine. Let us apply KVL to this loop. You can start from anywhere, let's say here. Move clockwise. The first plate you are coming across in the capacitor is Q. So the potential change across the capacitor will be minus Q by C. Continue moving along the loop. Then you will come across the resistor and you are moving across the resistor opposite to current. Current is flowing to the right side through the resistor and you are moving to the left. So you'll have to take potential change as plus IR is equal to 0. So you can simply write Q by C is equal to IR. Okay. But our aim is to get charge as a function of time. Okay, so you need to bring time into this equation. Can one of you tell me how to Include time in the equation.
Sir, dq will be I into dt.
So you are saying I is equal to dq by dt.
Yes, sir.
Okay. This is not correct here. Yes, why did you say I is dq by dt? Or like on what basis did you say? On what basis? What logic did you use to say I is equal to dq by dt? Is it from the definition of current or is it some other idea that you used?
Yes, sir. Like from the definition.
Okay. See, current by definition is rate of flow of charge. Fine. So here I is the rate at which charge flows through that wire. That's fine. But here we have assigned the symbol Q to charge on this plate of the capacitor, charge on the left plate. Okay. Now, if current flows in the direction that is shown in the diagram, what happens to this Q? Does it increase or decrease?
It decreases, sir.
It decreases. So Q is a decreasing quantity. If current flows this way, Q is a decreasing quantity. Okay, decreasing value. Anything that is decreasing, its rate of change will be negative.
Negative. Yeah.
Okay. But we have taken current in that direction, and current in that direction is positive, right? Then how to make the equation correct? You have to take I is equal to minus dq by dt here. Because Q is a decreasing quantity. Current here is positive. In this direction, the current is positive. We know that. You have to express it in terms of charge on that plate of the capacitor, and charge on that plate of the capacitor is a decreasing value. So you have to take I as minus dq by dt. We are not changing the definition of current. Definition of current is still current is rate of flow of charge. But the rate of flow of charge in that wire will be equal to negative of rate of change of charge on the capacitor plate. Okay, that is what we are writing in this equation. Is this clear to all of you? Any doubt in this? Okay. So just make that adjustment here. So you get Q by C is equal to minus R dq by dt. And then keep the Q terms on one side, T terms on the other side. You get minus RC dq by Q is equal to dt, or you can send the minus RC to that side. Integrate both sides. Integral dq by Q is ln Q. Limits initial charge to charge at a random time t is equal to, this becomes minus t by RC, 0 to t. So substitute limits, you get ln small q divided by capital Q. Ln small q minus ln capital Q, that is ln small q by capital Q, is equal to minus t by RC. RC, I'm writing it as tau again. So you get Q is equal to capital Q e power minus t by tau. That's all. As the equation suggests, this is an exponentially decreasing charge. And then we know that in this case, I is minus dq by dt. You do the differentiation, you'll get the current also as a function of time. How much does it become? Put the minus aside, differentiating this, capital Q is a constant. Derivative of e power minus t by tau is minus 1 by tau e power minus t. Okay, minus t by tau. And we know tau is equal to RC. You can substitute that if you want. Minus minus cancel. It becomes Q by RC e power minus t by tau. That is the current as a function of time. Current is also exponentially decreasing. Why will current be exponentially decreasing? Let us understand. Initially, the capacitor had charge, significant amount of charge, means it has significant amount of potential difference across its terminals. Now the capacitor is connected to the resistor. So whatever voltage is there across the capacitor, the same voltage will be across the resistor, which will drive current through the resistor. Now, as the capacitor gets discharged, this value will decrease. The voltage across its plates will decrease. That means the voltage across the resistance will decrease, and therefore the current will decrease. Okay. And once the capacitor is completely discharged, means once all the minus Q has combined with the plus Q, there is no further charge to get combined. So there won't be any further movement of charge. Current becomes zero. Okay. That is what is discharging of a capacitor. The only thing you need to be careful about while solving questions based on all these is the resistance they use, because students in a hurry, they tend to like use the equation that they have learned. Okay, this was a problem. Let's go to the derivation that we did here. Yeah, we got current as I is equal to V by R e power minus t by tau, charging equation. Okay. We got this equation because the battery voltage was V and resistance in the circuit was R. Now in the question, they may call the resistance, take resistance as 2R. Then you can't use this equation. Then you will have to write V by 2R. Okay. Such changes are what you need to be careful about. Fine. That is all there is to know about charging and discharging of a capacitor. And the important thing to remember is the behavior of a capacitor when it is uncharged and when it is fully charged. When it is uncharged, you treat it as a wire. When it is fully charged, you treat it as an open circuit or open switch. Okay. To find out the currents, potential differences and all. Okay, I'll send you a worksheet based on this. And tell me how many of you want me to explain those cube resistance questions. If you want that, then we'll discuss that on Monday. Otherwise, we'll start next chapter, moving charges and magnetism, on Monday or Tuesday.
Can you discuss those questions?
Okay, fine. So, yeah, Monday's class itself, maybe like a half an hour or 40-minute class I'll take. In that we'll discuss. Tuesday we'll start moving charges and magnetism.